Hello guys, welcome to the chemistry lesson. In today's chemistry lesson, we are going to look at the last part of organic chemistry, which I didn't cover in other lesson. All right. So before I do that, let me just bring my highlighter, which I've not brought on board, so that it can help us move along together. Okay, so I think my highlighter, let me put it at 20 like that, and then apply like that, and then let me put the opacity maybe at 125 like that. Okay, all right, so I'm saying in today's video we are going to continue with the last part of organic chemistry, which I didn't complete, which is actually looking at natural macromolecules or polymers. Remember, we have two kinds of macromolecules, which are number one, artificial macromolecules or synthetic macromolecules, and then two, we have what we call natural macromolecules or polymers. So here we must understand that natural polymers are polymers that occurs naturally in living organisms. All right, so these are just polymers that are found in living organisms. All right, so here we are saying examples of natural or biological polymers are carbohydrates, proteins, and the fats. So these are the common natural polymers that we come across in chemistry. All right, so we are saying all natural polymers are condensation polymers, okay, with some exception, of course, of fats here. All right, so now we will talk about now carbohydrates as natural polymers in terms of their monomers. We'll also talk about in terms of how actually these monomers form, to how these monomers join to form a carbohydrate, a polymer, and also other small reactions that carbohydrates undergoes, like hydrolysis. So here we are saying that carbohydrates are natural polymers, each with a large number of sugar units, which are glucose joined together by oxygen atoms. Yeah, so these carbohydrates we are talking about are just natural polymers. Now, in each, there is a large number of sugar units. So you find that there are small sugar units or glucose that join together by oxygen atoms, or that are joined together by oxygen atoms. You are going to see what this means here. So we are saying one of the most important monomers in the carbohydrates is glucose, represented by the figure shown below. So this is glucose here. All right, so this is glucose actually. So a glucose molecule will consist of two hydroxyl groups at each end. Okay, so there's a hydroxyl group here and also a hydroxyl group, and this block here represents actually a carbon chain. All right, so this is actually a glucose molecule. All right, so we are saying this is actually a glucose carbon. This one is a carbon chain, while this one is a glucose molecule. So this is how we represent the glucose molecule in short form. So this is a monomer of carbohydrate. Okay, so I've pushed it here. So we are saying hundreds or thousands of glucose monomers undergo condensation polymerization reactions to form a polymer of carbohydrates as shown. So these monomers here, we would join in a reaction called condensation to form a polymer of carbohydrate as shown. So here we have, for instance, one glucose, which is a monomer, joining with another glucose monomer, another glucose monomer, another glucose monomer. So here we have only given 1, 2, 3, 4, but these join in hundreds or thousands. When they do so, then they form a carbohydrate polymer. So this is just a simple example. So for instance, now when they are joining, you find that one glucose monomer will lose the hydroxyl group, while the other one will lose the hydrogen. So this one on this other end, so you find on one end it should lose the hydroxyl, okay? Like here, this one will lose the hydroxyl, then this one will lose the hydrogen. But this one which lost the hydrogen on this other end, it is losing the hydroxyl. So it remains there with the oxygen. Here it lost the hydroxyl. This one will lose the hydrogen. So this one here will lose also on the other side the hydroxyl, and this one will lose the hydrogen. So you find that this hydroxyl and the oxygen, when they join, these form water, this form water, and this form water. So here also this, since here it lost the hydroxyl, here it loses only the hydrogen. Also this one loses the hydroxyl here, all right? So now this also with that they join. So what happens is this, when this happens, so what is formed is this. So this now, actually there was an error. This one is not supposed to be there. So let me just edit it quickly so that we see the correct stuff here. Okay, so, okay, I'll just leave it like that. So this one was supposed to just be the bond here, because this will be lost. There was just supposed to be a bond here. This oxygen is coming from here, so just understand that. So this one now, consider this as coming from here. This is oxygen, which is here. So here only this bond came. Okay, also here, consider that only this part came. Okay, all right, so here there will be only this in the middle. Also here there will be only this in the middle. Okay, so on one end there will be the oxygen atom, on the other end there will be nothing. So that's now how this forms. So this one, actually, when this form, there's an elimination of water molecules. So water molecules eliminated, like this and that, they'll form water molecules, and this is. So in this case, we'll have how many water molecules? Like this with this 1, 2, 3, 4 water molecules are eliminated for every 4 glucose molecule. 4 water molecules are eliminated, so to form this. So this one will be actually this bond here, this thermal bond here, or links. These are called the cellulose link or glycosidic links. This one here, all right. So now the whole of this one is what we call either the glucose molecule or starch molecule, which has now been joined by small monomers. These, they join together to form the large monomer, which is carbohydrate. So this is how the carbohydrate is formed. So you need to take care of it. Then we are saying starch and cellulose are 2 examples of carbohydrates that are polymers composed of glucose monomers. They are called polysaccharide. Okay, so saccharide mean one glucose. So when they say they are called polysaccharide, poly means many, then saccharide means glucose. All right, so here we are saying polysaccharide means many saccharides. Okay, so that's what it means. So like we have seen in the previous one, when many saccharides they joined, they form a polysaccharide, and that polysaccharide can either be starch or cellulose. So here we are saying when 2 glucose monomers join, they form maltose. So maltose is a disaccharide as shown below. So a disaccharide as shown below. So if we have this glucose and with another glucose they join, then what happens is, as usual, this will lose the hydroxyl, this will lose the oxygen. Also, when these two react now, they will join after losing this. So water molecule eliminated. Okay, this should have been water molecule, guys. So let me just control it. Okay, so water molecule eliminated. Then once water molecule is eliminated, these they join. So here there will remain nothing. Here there will be this. Then it will join like that. So now this which they form, this, the joining of two, when two glucose or glucose monomers join, they form maltose, a disaccharide as shown below. So they form now when these two join, they form this whole thing they join here. It is called a maltose and it is a disaccharide, meaning it consists of two saccharides or glucose. So here we are saying carbohydrates contain carbon, hydrogen, and oxygen in the form like CX, then H2Y, then OY, where X is a multiple of 6. So that's how it is. So you'll find that the number that like Y will contain here, if it is 2, then here it will be 2 times that Y, which means it will be like 4. All right. Then usually this carbon here will only have a multiple of 6. So meaning it can start from 6. We can say if we have carbon like 6 here, okay, then we can have like hydrogen. We don't know this hydrogen here, right? Then here, let's say we have Y. So if Y we have 6 here, we know that Y is 6. Then it is possible to know what will be here to mean that 6 times 2. So here it will be 12. Okay, so this is actually like the general formula of carbohydrates. Okay, so that's why they're telling you to say carbohydrates contain carbon, hydrogen, and oxygen in the form CX, then H2Y or Y, where X is a multiple of 6, meaning X can be either 6 from 6, you can have like 12, okay, it can either be 12, then also after 12 it can either be 24 or rather 18. From there it would be 18. The multiples of 6, the numbers in which 6 can go. So that's how it moves. You can start from 6, 12, 18, not 16, but 18 there. Okay. So that's how it goes. All right. Then we move on. So here we are now looking at hydrolysis of carbohydrates. So hydrolysis is one of the reactions which carbohydrates undergo. And then here we are saying that hydrolysis is a reaction in which molecules are broken down by reaction with water. So molecules can get broken down when there is water in the presence and some other conditions. For instance, here we are saying acid hydrolysis of starch is one way carbohydrates are hydrolyzed. So there is acid hydrolysis, which is one way starch is hydrolyzed. Okay, so acid hydrolysis of starch is one way carbohydrates are hydrolyzed. So we are saying when complex hydrocarbons, when complex carbohydrates are heated with dilute hydrochloric acids, they are hydrolyzed to sugars, meaning that when complex carbohydrates or large carbohydrates such as starch or cellulose are hydrolyzed with dilute hydrochloric acid, Okay, we are saying when they are heated, of course, when complex carbohydrates such as cellulose or starch are heated with dilute sulfuric or hydrochloric acid, they are hydrolyzed, meaning they are broken down into sugars or glucose, or they are broken down to their monomers. All right, like in this case, if you have starch plus water, so in the presence like of, let's say, sulfuric acid here, so this starch and water in the presence of sulfuric acid would lead to formation of sugar or starch. So we are saying the above hydrolysis, this reaction here is summarized in the figure below like this. So if this was the starch that we have, okay, so let's consider this as starch. So this starch. So we are saying this starch here. So let's push it here. This is starch. So it is here now. We are saying can undergo hydrolysis. For instance, we have one type of hydrolysis, which is the acid hydrolysis. So if starch undergoes acid hydrolysis, it should give us sugar. So we have sugars. There are how many monomers of sugar here? 1, 2, 3, 4. So all of them will be broken. So we'll have this one and this one, this one and this one. All of them now, they will be 1, 1, 1, 1. Okay. So also this, it can also undergo another type of hydrolysis, which we call enzyme hydrolysis. But if this starch undergoes enzyme hydrolysis, it is broken by an enzyme. It usually go to this. It forms what? Maltose. So this one is maltose. So this is one maltose and this is another maltose. So this one we are saying glucose, which is this is the formula for glucose. This is maltose. So maltose, this is the formula. So once this is 11, this should be 24. I mean 22. So this is 12. All right. So this is maltose. This is glucose, and this is the formula for glucose. You need to know it. Maltose, this is the formula for the maltose. Then we can move. We are saying sugars formed by the hydrolysis of complex carbohydrates can be identified using chromatography. Yeah. So these sugars that can be formed from hydrolysis of starch can be identified using chromatography. All right. Then we move on to proteins. So proteins are another type of natural polymers. So here we must understand that proteins are natural polymers, each with a large number of 20 different amino acids joined together by peptide link or amide link like nylon. Yeah. So very, very clear. So proteins are just natural polymers, each with a large number of different or 20 different amino acids. So you find in a protein, it will be made of a large number of 20 different amino acids that are joined together, okay, by peptide link or amide link like nylon. So you find that the links that are found in a nylon, which is a synthetic macromolecule, are similar to those that are found in proteins, which is a natural uh, macromolecule. So you need to take note of that. Okay. So here we are saying the amino acids are the monomers, all right, of proteins. And an amino acid contains a carboxyl group at one end and an amide or amino group at the other, as well as a carboxyl, carbon side chain represented by R as shown by a general formula below. Yeah, so what is being stated here is that this amino acid itself, which is a monomer of protein, contains carboxyl group at one end and an amine group at the other, then as well as carbon side chain represented by R as shown by the general formula below. So an amino acid will look like this. It will have on this side here, okay, which I didn't indicate. On one side, it will have this, okay. This is an amide group or amine, okay. Then on the other end, it will have this one here. This is a carboxyl group, the COOH. Then it will have also a side chain of carbon, a carbon chain here. So this side will contain a carbon chain, which now is represented by just R. This is what this statement is saying, that the amino acids are the monomers of proteins, and an amino acid contains a carboxyl group at one end. This is the carboxyl group, and an amine group at the other. So this is an amine, all right, as well as a carbon side chain. So this is a carbon side chain represented by R. Okay. So now we continue. So here we are saying this whole thing here, let me just clear. So this whole thing here is an amino acid. Okay, so an amino acid is a carboxylic acid with an amine, which is NH3. So N1 and H2. So NH2. So this one is represented in short as an amino or amine in the form of NH3 functional group. So then R stands for the rest of the molecule or group, this one here. So now here we are saying there are 20 common amino acids. So in nature, like we exist, we have like more than 20 common amino acids. So here are the three of the different amino or different types of amino acids. Namely, we have glycine, then alanine, and then cysteine, like these. So glycine, alanine, and the cysteine or cysteine, like this. So this one is glycine, this one is alanine, this one is the cysteine, this one here. So these are the three examples of the amino acids that are there of the 20 common amino acids that exist. These are just examples. So now the reaction below shows the formation of a polymer of protein from 4 different amino acids by condensation polymerization, like here. So like if we have different amino acids that can form this one, this one. So these are different. They're differentiated by the carbon chain here. This one is different from this one, from that one, from that one. So these are different amino acids. So there are 4 of them. So when they join it, they can form a protein. How? So this amino acid will lose the hydroxyl group. This one will lose the hydrogen. This one the hydroxyl. This one hydrogen. Here the hydroxyl. Here the hydrogen. So you would find that once this happens, then what happens? A protein will be formed. Water molecule eliminated. So there will be water molecule like 1, 2, 3 water molecules will be eliminated. Okay. So you find that even this one here can come out, this hydrogen, and this one can come out. Usually that's what would happen. This can come out and this one can come out, so that what is formed, like this, should come out as well. So that what is formed is this one here. So let me just do like this. Let me just remove this. I understand this should come out. This bond has to come out. This one also. Yeah. Yeah, that's how it should be. Yeah. So this one also comes out and this one, so that this one can be like that. So this one will be like that. So we have picked this, we have seen this and this. So this one can come out, so it will be like this. Why it is coming out? Because even on this one, it is coming out, even this. So this and that should form water, okay? So there will be this water, this water, this water here, plus that there will be like 4 water molecules, like 1, 2, 3, then this hydroxyl and this, they'll form water. So like also this one, when it loses this, it will come like that, okay? It will join in there. So this one comes to join here. This one comes to join here, as you have seen. This part here is this part here joining there. So again, this one part can come and join there like that. So again, this part can join there like that. Okay. So now, this one now, the whole of this one, which is formed when these join, it is called the protein. So this is an example of how a protein is formed. So it will have now these, which are common. These are links. This is a link, the joining point. Here, this is the joining point, which is this and this and this. So we have a 3 joining point, 1, 2, 3, 1, 2, 3. Okay, this one here. So I've only labeled this one for a reason. So this one here, it is called the amide leakage, as in nylon. So it is the one which is also found in nylon. All right. So you have to take note of this. So sometimes you would discover that these H C carbon, H carbon, and this can be represented by a block, and also here by a block, just, and this one by a block, and also this one by a block. Then if that is the case, meaning this can look similar to that of nylon structure that was covered in the last video on organic chemistry. All right, so we move. So we are saying 60 to 6,000 amino acid units can join it to make a macromolecule of protein. Yeah, 60 to 600 or to 60,000. So this is a big number, all right? So 60 to 6,000 amino acid units can join it to make a macromolecule of protein. So they can be different amino acids joined in different orders. So these can be different amino acids and then they're joined in different orders. So there are a huge number of proteins out there, all right? So we have different type of proteins, guys. When we talk of proteins, usually we think there's only one type of food protein. No, there are so many different types of food protein resulting from different orders in which amino acids can join, okay? Then let's look at hydrolysis of proteins. So we are saying protein plus water in the presence of water boiled with a hydrochloric acid, it can give amino acids, meaning protein can get broken back to amino acids if you want. So it's like digestion in reverse, like what digestion does. Okay. In other words, it's like digestion here. This is like digestion. So we go to fats. So we are saying fats are well-known macromolecules which are not polymers but esters because they are made from an alcohol and a carboxylic acid. Yeah. So in this case, fats have been classified to be, though they are under natural macromolecules, but they are not polymers as such. All right, because they are not polymers as such, because they are made from an alcohol and a carboxylic acid. So there will be like few. there will not be many alcohols and carboxylic acid, there will be like few. So the alcohol is always glycerol. Okay, that's what you should know. Alcohol is always glycerol, a natural alcohol with so this glycerol is a natural alcohol with three hydroxyl groups. Its chemical name is propanol 1, 2, 3 triol. So this glycerol, which is a natural alcohol with three hydroxyl group, has a chemical name propanol 1, 2, 3 triol. Propane 1, 2, 3 triol. Okay, so now we can now look at an example in terms of the diagram. So this is a glycerol, which is a natural alcohol with what? With three hydroxyls, which are the OH, which is 1, 2, 3 of them. So this is a glycerol. You need to memorize it. So we are saying this one here is a molecule of glycerol. So we are saying the acids. So we have talked about the alcohol part which form the fats. Now we are going to the acid. So we are saying the acids are natural carboxylic acids. Okay, so these acids are natural carboxylic acids, usually with long carbon chains. So they'll have long carbon chains. They are called fatty acids. So for the carboxylic acids that are part of the fats are called fatty acids. For example, we have palmitic acid with this formula here, C15, then H31COOH. So you see this is the carboxyl group. So meaning this is an acid, a natural acid, which is the palmitic acid. All right. So it will have like a carbon chain. So this is a very long carbon chain. Okay. So now we change the color. So we are saying the reaction below shows the formation of fats between fatty acids and glycerol by condensation reaction like this. So you will find that if you have this represents a carboxylic acid like palmitic acid, so it is reacting like with a fatty, with a glycerol. So this is a glycerol. This is like a carboxylic acid, which is a fatty acid. There are three of them actually, 1, 2, 3. Okay, then here we have one actually glycerol here. Okay, so when they react, you find that this will lose the hydroxyl, this hydrogen, hydroxyl, hydrogen, hydroxyl, hydrogen. So this they'll give water molecule. Okay, so water molecule is eliminated. So there'll be how many water molecules? 1, 2, 3. So this is it. 3. So we put -3, meaning subtracting from these 3 water molecule. So when a water molecule is lost, these they will join, like this one here. This is this one here. So this oxygen is that one here. So they will join here, join there, join here to form this. Now this group here, this link here, which is common here, this is called the ester link. So this group is called an ester linkage. So when you are asked like which natural molecules has the same linkage as the ester linkage, it's just the fat. Okay, so here this is what we said in form of an equation. 3 molecules of fatty acids, 1, 2, 3 molecules of fatty acid are reacting with 1 molecule of glycerol to form. This will be 1 molecule of fatty acid. Here we should have also put plus water because 3 molecules of water are also eliminated or formed. So then we are saying R, this one here, or boxes, stands for the long chain. So this R stands for long chain of carbon atoms with hydrogen atoms attached in the acid. So here, this is the acid. There will be a long chain of carbon with its hydrogen there. Then we are saying each hydroxyl, like this one here, in a glycerol molecule can react with a different fat acid, like this one, hydroxyl with a different fat acid. So each hydroxyl in a glycerol, like this hydroxyl, I mean in the glycerol here, can react with a different fat acid. This one with a different, this one a different, this one a different. So in this glycerol, each hydroxyl, like here, can react with a different um, a different fat acid. So you can get many different esters, not the ester linkage, as in pterine. So this ester linkage is also like that in pterine that we looked at in the previous video on organic chemistry. Okay, so this diagram which we have done here, this one here, this one, these are represented by boxes. So either arrow or boxes. So this is the next diagram here. So you have seen some, these are boxes, those arrows. So this is a different form. So this is water, the same water. So this is the same glycerol molecule. So these are different. So I decided to write this so that you get to see different forms. So this and this one here, they're just the same, except that this one has been written with these boxes here, and these hydrogen and the hydroxyl group are written in different format, but this is the same. So this is the fat which will be formed, okay, which is one molecule of fat, this one here, and then water, 3 molecules of water. Then we are saying hydrolysis of fats. So fats also can be broken down to their constituents. Like we are saying, fats can be hydrolyzed by heating with aqueous sodium hydroxide, giving fatty acids and the glycerol as shown. So let me push it here. So if you have hydrolysis of fat acids, you have this, which is a fat. So this fat, you react it with the sodium hydroxide. You find that the 3 molecules of, 3 moles of sodium hydroxide react with this fat here. You find that it will be broken down. This will be broken down back into, it will form now this. This will be a salt, okay, and a salt or a soap plus this one here. This one will be a fat, glycerol. So this one we're saying the sodium salts or fat acids are used as soap. So this will be like a fat acid but with sodium attached to it. So there will be sodium atom attached to it. So this one is called sodium salts of fatty acids, and this is used as soap. So soap is made in factories by boiling fats and oils with sodium hydroxide as above. So if we want to make soap, we can just get fats or oils, boil them with sodium hydroxide, then we'll be there forming soap. So for example, we are saying, this is the same reaction that I've already looked at. Like if you have an ester in vegetable oil, this is vegetable oil plus fatty, sodium hydroxide, you form this glycerol, and you form this other one here, 3R, which is the soap, the sodium salt of fatty acid, this one here. So we are saying the soap, which is this one, you buy may be made from vegetable oil like palm oil or coconut oil, or even from fish oil or animal fat. Okay, so we are being told now that the soap we buy may be made from vegetable oil like palm oil or coconut oil, or even from fish oil or animal fat. Chemicals are added to make it smell nice. So these are usually artificial esters. So esters would be added to this because they have got a nice smell. And when they are added to that, soap starts smelling good and we like it is not coming from fats, when in fact it is coming from fats. Now, this method is called saponification. All right, so we have come to the end of this organic chemistry lesson here. So we have completed the organic chemistry lesson. We have done the last part. So I hope you have understood and enjoyed this. Wishing you all the best in your exam as for now. Bye.